Okay, today with 6.6 notes, we're talking about solving exponential and logarithmic equations. Well, we know that exponential equations are those equations that deal with exponents. So it might be 2 to the x power equals 4 or something of that nature. And by that same logic, a logarithmic equation is going to be using a logarithm. Now, I think our intuition pretty much helps us understand the property of equality for exponential and logarithmic equations, but it's telling us that if b is a positive real number other than 1, then b to the x power equals b to the y power if and only if x and y are equal. Well, that makes sense because if the bases are the same, that means that the power they're raised to has to be the same. Otherwise, they wouldn't equal each other. They would be different values. So, for example, if 3 to the x is the same thing as 3 to the 5, then we know that x is equal to 5. And alternatively, if x is equal to 5, then we know that 3 raised to the x power is the same as 3 raised to the 5th power. And that also applies to the property of equality for logarithmic function equations. So if b, x, and y are positive real numbers where b is not equal to 1, then the log base b of x is equal to the log base b of y if and only if x and y are the same thing. So if the log, for example, if log base 2 of x is the same thing as log base 2 of 7, then it stands to reason that x is equal to 7. Or that if x is equal to 7, then we know that the log base 2 of x is equal to log base 2 of 7. So that's kind of just trust your gut on that and your intuition. We know that if those bases are the same, then we need to have those equal values, otherwise they won't maintain a balance. So let's go through some examples, and I'm going to go through these fairly quickly, but feel free to pause the video, rewind the video if you need to make sure that you're getting what you need out of it. So for the sake of this, I'm going to, you don't have to write down everything I write down, but my thoughts I'm going to write in green, and then my work I'm going to write in blue so that you can kind of see what I'm seeing. So when I look at this, the first thing I notice is that both have a base of 5, so I can set my exponents equal. Okay, so that's my note to myself. That's me talking about what kind of strategy I'm going to have to solve this problem. So I look at my exponents and I say, okay, well, 2x plus 4 must be equal to 5x minus 8. And then I'm going to solve this much the way that I've been solving since middle school. I'm going to gather up my x's on one side together, and then I'm going to get rid of the things that don't belong with it until I get a single copy of x alone on one side. And that tells me what my x value is. If it comes to the point where I need to round, I will round to the nearest hundredths place. Okay, my thinking is going to have to shift a little bit on number 2 because I'm not faced with two I'm not faced with two different bases that are the same. As a matter of fact, there's only an exponent on one side. So what I start thinking of is, well, what undoes that exponent? I know that a log is going to undo an exponent. So I know I'm probably going to be using a log here. So let me go ahead and start by rewriting this in logarithmic form. So my log has a base of 5. So log base 5 of 42 equals x. Well, that's good news because I have the x alone on one side, a single copy of it, just like I want. But to put that in the calculator, I'm telling myself, probably going to want to use my change of base formula. So if we remember from the notes just yesterday, I believe that's in 6.5, that tells me that I'm going to enter in the log of 42. Make sure I close my parentheses whenever I'm given the opportunity there, divided by the log of 5, and that will give me whatever my x is to. And if I plug that into the calculator, I'm going to get x is equal to about 2.32. The next one is very similar. I'm looking at it, and I feel like the same steps are going to kind of be in place. I know that I'm going to use a logarithm. because it will undo my exponent. So my log base is 3. So log base 3 of 5 is x plus 3. Well, I notice here that I last time I got all excited because my x was alone in a single copy by itself, but here it's not. So I need to go ahead and handle that first. So what I have is my log base 3 of 5, all of that, and then I have to take the 3 away from it, will equal x. So I believe I'm ready to put it into my calculator. So I'm going to remember my change of base formula. So what I'm going to enter into my calculator is the log of 5 divided by the log of 3. Now once that gets calculated in my calculator, then I'll subtract 3 from it. And I do that, and I hit enter, and it will tell me that x is approximately negative 1.54. Moving on to number 4, I do notice that I have the same base again, so that's good. So I know that they both have a base of e, so I can set the exponents equal. That to me feels like probably the easiest type of problem. So I've got my 2x minus 1 and my x plus 2. So 2x minus 1 equals x plus 2. Again, I'm going to gather my x's together on one side so that I have x minus 1 equals 2. And then I want to go ahead and isolate my x. So I have one single copy. X equals 3. Okay, when you go ahead and turn the page, we've got a few more examples that use exponents, and they're going to be just slightly different. You'll find a few little things that are different, and it'll help you be prepared to deal with any situation. So I'm looking at this, and I see that it's an exponent again, and I probably don't want an exponent, so I know that my log will undo an exponent. So that's my first strategy that I'm going to deal with. So log, my base is 2, 108 equals 4x. Well, x is not alone, so I want to get rid of that. I know that my x is going to be equal to log base 2 of 108, and all of that is divided by 4. So x is alone, I've got a single copy. That's good news. But before I put it in my calculator, I want to remember that I might need to use that change of base formula. So when I put it in my calculator, it'll actually be log 108 divided by log of 2. Remember to close those in. And once I get that, I'll divide that whole answer by 4 to get my final result. Number 5, I'm thinking, well, when I'm solving for anything, I can kind of foresee that I'm probably, again, going to want to use a log to get rid of my exponent. But before I do that, I need to get the e all by itself. I need to get it alone on one side, or with its exponent. So I'm going to go ahead and divide by 12 on both sides. So on the left side, I'll be left with e to the 1 minus x power equals 500 divided by 12. Well, I know that instinctively a lot of you immediately reach for your calculator, but I'm going to say don't even bother doing that yet, because the earlier you round and the more often you round, the less accurate your answer becomes. So I'm just going to keep mine like that. I mean, you could reduce it down to 125 over 3 if you want, or you can leave it like this. But I know that the log is special when it comes to an e. My log base e is actually the natural log. So I'm going to take the natural log of both sides. So that cancels out on that side. And this moves down. We did that power yesterday. So 1 minus x equals the natural log of 500 divided by 12. It's almost alone. So what I'm going to do is I'm going to subtract the 1 from both sides. And then finally, I need to get rid of that negative 1, so I'm going to divide by negative 1 both sides. That effectively changes the sign of each of these terms. So it'll now be a negative. Natural log of 500 over 12 plus 1 that can all be put inside of a calculator and get a result that I'm going to go ahead and round, and should be negative 2.73. Remember, if I'm moving too quickly, you can pause and rewind this video as many times as you'd like. So instinctively, I remember over here that I wanted to get my e alone first. So I'm going to do that first. I'm going to add 14 to both sides. So I'll have 3 to the ex equals, well, 11 plus 14 is 25. And then still not alone, got a little work to do, so I know the e to the x. And again, don't reach directly for your calculators, just wait, we'll round at the end. I know that to get rid of that, I want to take the ln of both sides. That cancels that out and moves that x down. So I've got x equals the natural log of 25 divided by 3. If you put that into your calculator, x will equal 2.12. So we've done ones that had the same base. We've used a logarithmic or an exponential to a logarithm. We've remembered our change of base formula. We remembered to isolate the variables. Now we're going to do pretty much the same thing, only this time we're going to be dealing with logarithms, and we're going to see that really it's the same rules apply. So I'm looking at this and I see a log, and I remember that to undo a log, I need to make it an exponential. So an exponential will undo that. Okay. So my base is 3, and I know that my logarithm yields my exponent, so 3 squared equals 4x plus 1. Well, I've been solving ones like this since middle school, so I'm just going to go through my inverse operations until I can isolate a single copy of x alone on one side. And there you have it. Now on the next one, what I do notice right away is that they've got the same base, so I can set them equal. I can set that equal. Let's see, we've got x squared plus 3 on this side, and on this side I've got 4. I use my inverse operations. And remember, sometimes it's going to be, because I use that square root, I know that it could be plus 1 or minus 1. So again, I'm looking at a logarithm, and I want to undo that. So I'm going to be thinking of my exponential form here. So I know that I can't see a little number down there, so I know that that's my common base of 10. My common log of 10 squared equals 3x minus 5. So 10 squared, I can just perform that calculation. And then I can start trying to isolate my x, a single copy on one side, by using inverse operations. And there you have it. Again, feel free to pause or rewind this video as you need to. What's different about this one is that, yes, I do have 2 natural logs, but it doesn't set them equal. One's not on one side of the equal sign and the other on the other with nothing else there. Here, they're both on the same side and they're set equal to something completely different. So I'm going to go back to what I learned in the last lesson, which was 6.5. And I'm going to condense these. I'm going to condense my logarithm, or my natural log here. So that means I remember that I see a plus, so I know that I can express that with multiplication. So I'm going to write ln one time. I'm going to multiply my 3 and my x plus 2. So if I take 3 to the x, that's 3x. If I multiply 3 to the 2, that's 6 equals 4. Well, now I have a natural log, but I want to get that x out of there. So I know that that I need to take e to both sides, or I need to multiply both sides by that base e. And that cancels out here. Oh, let's do that like this. Change that color. I'm going to be consistent. And I'm trying to isolate my x, so I'm going to use my inverse operations. Again, working my way through that. So I've got e to the 4th minus 6. It's almost by itself, but I've still got that 3 multiplied to it, so that divides to get rid of it. And I've got e to the 4th power minus 6, all of that divided by 3. And all of that can be put in your calculator very easily. And you will come up with 16.2. Well, this one is very similar, but this time I see a minus there. So I know I can still condense because they've got that same log base 3, but it is a minus, so I know I'm going to write this out as division. Okay, and also I see that I have a 2 here that I can move over to be an exponent. So I know I'm going to want to move that 2. So that means I'm going to have 2x squared. Okay, well I think I can simplify that even more, because if I square the 2, I get 4, and if I square the x, I get x squared. So let me just rewrite this as log base 3 of, now that's 4x squared, because I moved my 2, and I simplified. So this is the problem as I see it now. And now's when I can do my condensing and move things back and forth. So I'm going to write my log base 3 just one time. And I'm going to take that first term, my 4x squared. I'm going to divide it by my second one, that 2. And that's still all equal to 3. Well, I can simplify this a little bit because 4 divided by 2 is actually just 2. So log base 3 of 2, I still have my x squared, equals 3. And I'm almost done, but I want to get that out of the logarithmic form. So I know that an exponent, that can undo my log. So if I rewrite this in its exponential form, my base is 3, my exponent is this 3 over here, that equals 2x squared. And then again, just with some simple calculations, I can start isolating things. So 9 divided, did I do that right? I didn't do that right. It's not 9. So everybody makes mistakes. Let's undo that a little bit, because what I did right there is I squared my 3, and I don't want to square the 3. I want to take the 3 times 3 times 3, so it's actually 27. And then I can go ahead and divide by 2. So I know that 27 divided by 2 is equal to x squared. So if I square root both sides, I'll find that x is equal to approximately 3.67. And again, sometimes if you make those mistakes, it happens. Just go back and think about it logically until you can find where you made your mistake and do it again. Okay, so we've done a lot of different examples of all the different types of problems you'll work with. And here is one application problem. And again, it has to do with money. It seems like a lot of what we do when we think of it in practical terms comes back to money. So let's look at this one. I know I deposit $300 in a CD that pays 4.5% interest. And it wants to know how long, so we're looking for the T. How long will it take to double my money if it compounds A, quarterly, or B, continuously? All right, well, I remember that my formula for quarterly is the amount I get will be equal to the principal times 1 plus the rate divided by the number of times it's compounded, taken to the number of times it's compounded times time. And I remember that the formula for this one is the amount that I'll end up times the principal, or equals the principal times e to the rate and time. Okay, so let's see what information we have. Well, we know the amount that we want to end up with is doubling our money. So 300 doubled is 600. And the principal that we start with is 300. The rate, it says, is 4.5%. So if I move the decimal over 2 places, I will have 0.45. And actually, let's do the time next. The time for both of these is what we're looking for, right? But one of them compounds quarterly. So what is the number of times it'll compound if it's compounded quarterly? There's 4 quarters in the year. So let's first start by seeing what would it be, what would we end up, how long would it take to double our money if we were going to compound it quarterly. So I know I've got 600 is what I want it to be. I start with 300 and I fill in all the other values that I have listed over here. And I can start by, let's go ahead and get rid of that 300. So I know that 2 equals, and if I put all of this stuff into the calculator, I'm going to kind of simplify it that way. I'm going to put that all into the calculator, and it's going to give me 1.01125, and that is still to the 4t. Well, right now I have an exponent. I have my variable up in that exponent, and I want to work with it in a way that I can get rid of it a little bit easier. So I know that my exponent can be undone with a logarithm. So let's write it as a log. So log, my base is my 1.01125 of 2 equals 4t. Well, I'm almost there. I know what 4 t's would be, but I need to know what just a single t is. So I'm going to have my log base 1.01125 of 2 divided by 4 is equal to t. So when I put that in my calculator, I'm going to remember to use my change of base. So I'm going to do my log of 2 divided by my log of 1.01125. And once I get that figured, I will then divide it by 4. Put all that in your calculator, and if you're rounding, you'll get about 15.49 years. That's my quarterly. But that's not all I want to do. What I want to also see is I want to see what it would be if it was continuous. Because I want to look at both of those. So I know that my A is still 600, my P is still 300, but I have e to the r t power, okay? I'm going to start the same way I started the last one. But I come to a place much more quickly where I need to go ahead and undo that exponent. Well, with an e, the way to undo an exponent is with that ln. So this cancels out and that moves down. So I have the natural log of 2 equals 0.045 times t. Almost finished. T is almost alone. Let's go ahead and divide to get that 0.45 out of the way. So I know that t will be equal to the natural log of 2. When I put them in my calculator, I'm going to make sure I close that up. Divided by 0.045. You can hit pause while you put that in your calculator. You'll end up with 15.4. So it will take you a little bit less time to get there if you're compounding continuously than it would quarterly. And that is it for Chapter 6 notes.